Hello, everyone. My name is Rick Hanslick with Alpha Technologies. I've been with the company just shy of 3 years now. My background is in chemical engineering, and today I will be hosting the webinar on rubber characterization for computer-aided design. The speaker is Rick Zeibel, and he is the Fellow of Technology for RDAbbott. Rick has been in the industry for a little over 37 years, and his specialty is organics and silicones. So at this point, I'm going to hand things over to Rick. If you have any questions, feel free to leave them in the comment or question section. And I also attach two papers from Rick that you are able to download for your own personal pleasure. So, Rick, take it from here. Thank you.
Thank you, Rick. Thank you very much. Just doing a check. Everyone see my screen okay? See my cursor? Yes? All right. All right, good. I always want to make sure that we have everything going. Well, welcome, everyone. Welcome. Yes, so we have two Ricks that are presenting for you. It might be easier if you just go by my middle initials, particularly shown here. Rick A. Zeibel, Raz. Yes, I'm often called by that in my early years, particularly in the swim teams and football teams that I played on. I am a speaker that is not involved with Alpha other than a good knowledge of their equipment because we have a number of Alpha RPA machines. My company is RDAbbott Company, and we're a distributor of products, both silicones and organics, rubber chemicals in general. My title is Technical Fellow and Vice President of Technology for RDAbbott. And here you see my email address and my office number that you can give me a call, or I'm sure you can contact me through Alpha. So I've been, serving the rubber industry for over 35 years. I'm a chemical engineer, and I have material science degrees. So that's an area of rheology that I've studied for most of my career, and I am so happy to have been involved with Alpha or one of their previous names over this past 35 years. Started out with the Monsanto Model 100 rheometer, of course, way back when, right? So, and then patents. I've got a number of patents that have been prosecuted, and I'm working on several others. They're around rubber compositions, particularly adhesion chemistry, which we use rheology a lot to perfect. So rubber instructor, I've been since 2007, rubber instructor for basic rubber technology and advanced subjects, including this one. So I'm very pleased today to be able to pull together a number of presentations I've put together over the last 5 to 10 years about this computer-aided design of items. And so let's, without further ado, let's get into it. A small advertisement about my company, RDAbbott. We use applied curiosity because curiosity is at the root of nearly every business decision and strategic action we take. It's how we approach every technical inquiry, every sales opportunity, and it's modeled in our genuine desire to serve our customers efficiently and effectively. And we are here today, me being a representative of my company, to really show you what is the curiosity of the day. And that is, of course, this idea of modeling materials for inputs to computer-aided engineering software. But I'm going to tiptoe through some ideas like designing for manufacturability and describe injection molding in that respect. We're going to cover rheology and injection molding parameter relationships. And then we're going to hopefully take a short break, probably close to the top of the hour. And then we'll come back and we'll really get into the meat of the subject. And that is the material characterization, viscoelastic behavior, oscillatory rheometer equations, and rheology testing profiles. So that's a real how-to cookbook session, followed by data fitting, which follows another real how-to cookbook section of taking all of the outputs of the rheometer and putting them actually into various software. And then I'll show you what the result of that good information comes to. So that's where we're headed. And I hopefully we'll have a good tour through this topic. If there's any questions, I know that it can be posted through chat and through the questions in the boxes. So feel free to ask me any questions throughout the time. Rick will, I'm sure, pause me from talking. I could talk all day long. So we'll definitely pause and let me answer those questions. So designing for manufacturability. Let's start the first section, section 104. First, I need to let you know what a rubber injection machine schematic kind of looks like and understand that this is a scheme of a screw and barrel connected to a runner system, with a mold. And the mold is heated for rubber materials, and the screw and barrel is generally cool to warm. There's a rotating screw which drives the material forward, places pressure. Of course, the viscoelastic effects of the raw material is very important in this. And then we fill the cavity of the mold. And in doing so, rubber is tortured. And this discussion is about having to measure that specific degree of torture and the feedback the rubber gives. So why is designing for manufacturing important? And I always like to start off with a big why. Why is CAE important? Well, the billions of dollars that are spent on injection equipment, and in large part, a lot of it's around rubber and plastic. 22%, so almost a quarter of the machines, and there's a couple of other items like machines for forming rubber and plastics here. There is about 25% of all the injection machines in the US are sold to this topic. And so billions of dollars are sold here. Putting your injection machine to the best use is really an endeavor that every fabricator manufacturer is seeking. And so design for manufacturing takes us through that. Let me describe what designing a manufacturing is, or DFM. We sometimes like to refer to it. And I do it by the responsibilities of the original equipment manufacturer, the OEM, the tool maker, that's the person that makes the mold, the company that makes the mold, and then the fabricator. And when we start up a new process, really, if you look at their responsibilities, the OEM has a big part of that. Toolmaker has a huge part, and the fabricator, of course, runs it. From there on, whatever was decided through these responsibilities is what carries forward in the manufacturing process. So designing for that manufacturing process is very important. And of course, it always starts with the assembly concept. In this case, I've kind of given you maybe a gasket of some kind in this assembly. And of course, that gasket has to be through the design concept. You know, how are we going to seal? Anytime you put two pieces of metal together, it's not going to fit perfectly well. So we're going to need some type of rubber in between. The next step of that is the part model. So once we understand the shape of this assembly, then we can start to draw out what that looks like. And here we see a drawing, and the part model is actually a computer-aided engineering modeling. It's actually something that in today's software, it's not just a print, it is a model, and we can look at it from a three-dimensional point of view. And those files are translatable between one piece of software and the other, and we can pull in one file across basis and then have a volumetric representation of what that part design looks like. Now, the OEM is responsible usually for both of these. Of course, so far, we really haven't covered DFM. So for the first aspect of DFM, we look at the first part proof, where we make usually a prototype mold, usually single cavity, just to make sure that this gasket is going to, in this case, seal between those two metal objects and actually create a proper seal. We might be looking at it in terms of the application fluids and temperatures and service requirements, but really the first part of that runs. And then once we have an approval, a thumbs up from the OEM, we transfer to the tool maker, and now the real designing begins. Because here we have to look at the cavity design. And in those cases, we are using things like MoldFlow, which is a CAE software, which shows us the flow of the materials throughout the material path in the injection machine, through the runner system, and through the mold cavity itself. And these are very important things because from the very get-go, we can look at process parameters, gating locations, defect analysis, and more. And then once we get that pre-production cavity design working on, then we got to go to multiple cavity design, because we're assuming that this is going to be millions of parts, right? And we want to do that efficiently. And we're going to be looking in that in terms of key quality characteristics, dimensional defects, cost estimation, cycle time, raw material usage, and everything else. And then ultimately, we look at the robotic operation and automating the process. Full automation is always the key for large production systems. And now, when we look at all of these 6 steps in DFM, we realize that there's a lot of importance that comes about from the computer-aided engineering concepts. We really see a lot from being able to take the part model and convert it over to a MoldFlow or a SigmaSoft or a MoldX 3D. There's a lot of different pieces of software that does this, and really analyze how the material will behave in that particular part configuration. And then when we get to multiple cavity design, it adds, an order of difficulty to that single cavity design, and so on and so forth. So I'm going to show you how you convert a lot of the raw material information in. So right here is where we do the CAE flow analysis. As soon as we've selected the material selection, I recommend that we start this type of analysis so that we have the material characteristics known up front. And then why is that important? Well, what if you don't do that? Then you really can't do cavity design and multiple cavity design. You really have to do it by iterative approach. You make a tool, it doesn't work, it becomes the so boat anchor, meaning, it didn't work, so tie it to a rope and throw it off of a boat, and you can keep the boat. Well, definitely a wasted expense there. Keep in mind that tooling in some cases can be multi-million-dollar items. So you want to be able to do it right the first time. Speed to market is very critical there. If you don't follow that program of looking at how to design the cavity correctly, you're definitely going to run into issues. And so I really recommend getting this material characterized. Now, in the rubber industry, how many compounds? Now, as I'm privy to that, I mean, we work with all the major rubber compounders out there, the Hexpol, the R&S Processing, all of these different companies, as well as the silicone side, all of those great companies out there. There are tens of thousands and thousands of active formulations all over North America. So you really can't expect the raw material supplier to take, 60,000 formulations and run material. it really is going to be up to the tool maker, the fabricator, the OEM to really get those things done. So the presentation today is about how to get that done. So the first aspect about getting it done is to understand viscosity and injection molding. The truth about rubber viscosity is the viscosity of a fluid is a measure of its resistance to deformation at a given shear rate, given rate of shear in mixing or moving the material through the screw and barrel. This is all shear rate dependent. Rubber compounds have rather high viscosities compared to other fluids. An injection press overcomes the viscosity by applying a mechanical force and puts pressure on the fluid. And then it creates behaviors of that rubber fluid, the material, the raw material. A good injection press applies forces in a very repeatable manner, but rubber changes its viscosity all the time and for many reasons. In fact, injection presses work in quasi or non-steady state, and that makes the rubber act in seemingly unpredictable ways, and I underline seemingly. And really, when you look at the viscosities of material and you look at what we typically look at, and I've put these in household items, anywhere from water, glass of water I have sitting here, very low viscosity, all the way up to, some of those very tough, high green strength, natural rubber SBR tire compounds, and even window glass. If you're staring out a window right now through my talk, know that window glass is also a fluid, but very, very high, 100 million Pascal seconds kind of numbers. And as we go kind of across this line, and I've got this arrow, the rubber process analyzer, the RPA, is really necessary. It's really got the motor, it's really got the die system figured out for measuring these specific high viscosity. And right around, 500 Pascal seconds in viscosity, measured, by the way, and I should probably footnote this, all these are measured at 10 reciprocal seconds. As we know, rubber is shear dependent. So all these numbers are kind of the 10 reciprocal second shear rate numbers that we see. It'd be a good thing to probably add up here. All right, so what is an RPA? Well, I'll tell you what an RPA is. RDAbbott owns several of these and works exclusively with alpha because we find that these machines can evaluate viscoelasticity. And that, I think, is the key word here. And I will be talking about the Premier system, which is a programmable system. And the programmable system really gives us frequency ranges, strain ranges, temperature ranges, all in a programmable manner that gets put into programs. And I will actually go through the specific programs today that can be uploaded to a Premier or other. They also have the ADT 1000 of the past and past instruments. And I just want to make a note about that. Rick is an expert on alpha machines. Raz is not. I'm a user of the machine. And I can tell you from this standpoint, they are very strong machines. We've had some for over 15 years performing day in and day out without ever missing a beat. And from a user point of view, I get great support from Alpha. So if you have specific machine questions, Rick is your person to discuss that with. If you want to know how to do material characterization, ask those questions of Raz, me. Okay? All right. So, all right. Well, that takes us in 19 minutes flat through the first important section. Excuse the noise in the background if you're hearing it. It's trash pickup day at my house. They'll be out just a little bit. But these meetings are always that, isn't it? So, what we're going to cover next, and DFM was really kind of a short subject, but if there's any questions out there on DFM or how all this applies to that, please ask now, and I can answer those questions as we go into section 2. And I'll take a pause to take a little drink of water. All right. So let's get into the rheology and injection molding parameter relationship and how we contrast materials, look at viscoelastic behavior in general, and injection process windows. The key of this is really the injection process windows. I just have to walk you through a few things in case you may not have attended some of the other lectures. And in this area, I'll be showing you some flow analysis and some things, some videos on the screen. I hope they come through okay. Sometimes there's a lag. Rick, you'll, I'm sure, check me on that. And so let's get started into this and go back to this idea of the rubber injection machine and what in the schematic concept, what that equals. And I've already covered this: screw and barrel, runner system, mold, cavity. But I also want to indicate now kind of the viscosity changes of the material as it comes through the material path, and kind of work through that. At first, we have, because of the sheer thinning of materials, we have a fairly high viscosity. And through the screw and barrel, there's a mastication process. This screw and barrel can turn faster and actually move materials back and forth and mix them. And some screw and barrel systems even have what they call a flight schedule. The movements change volume and push materials back and forth, creating shear heating and shearing in this system. And so we measure that. We also look at what happens in the nozzles as we try to constrict this flow of material. The shear rates go up. And then inside the mold itself, there's a number of runner paths in terms of delivery of material to each cavity, which would also create bottlenecks, if you will, and increase. So as we go all the way down the path, the viscosity is lowest at the end and highest at the beginning. And that's generally how that works. So I'm going to give you, first of all, probably the 25,000 foot view of why this is important. What you're seeing is a material A and a material B with setting mold temperatures at two temperatures, 160 and 180 C. And what we're seeing is the injection speed in the y-axis as compared to the injection pressure placed in this screw and barrel. So the injection press applies that pressure at the nozzle. Okay. And what we're looking at is the temperature in this cavity plate. So the temperature that's on the rubber material that's flowing in. And we're looking at two different material profiles. Now, these are just two same durometer grades of material. Happens to be silicone rubber in this case, because we do a lot of injection molding of silicone. But look at the dramatic differences that we see, how the machine has to handle that pressure input and the resistance of viscosity. These are two rubber materials that would once cured, you wouldn't be able to tell the difference between analytically in any way. I'm not comparing something like an SBR to EPDM. No, these are two silicone materials, and look at the dramatic difference in the behavior the press has to push this material through. And notice that the pressure is a force. I mean, this pressure and bar, we can see pressures that are tremendous, up to 200 megapascals or 30,000 psi type of numbers in these systems. So pressure is major, and the material's flow behavior is very dependent on that machine's performance. And so from the high view, we can see that, if we're going to do a cavity design and we're going to use CAE, we really need to characterize the specific material we're using. We can't go to a standard library and use, an EPDM formulation, even though we're molding a nitrile. Or we have to be able to characterize that specific compound, that specific qualified material for that specific application. And if you ever change, you have to re-qualify it. And part of that should be the material qualification under DFM, because you have to design for manufacturing. Now, I want you to understand this process, that the viscosity of the material is a function of temperature, shear, and cure. Always, we have these three different aspects to identify where the rubber is at any given time through the injection process. The screw and barrel is going to be run at a different temperature than the mold. There's different shear rates in the screw and barrel than and the shear history of the material as it flows through the path is very important. And then, of course, rubber cures. And as it does, it cross-links. And the viscosity starts to go up. And, you know, we are always looking at efficient processes in the fabrication process. So we don't start with a cold mold, inject the material, and then heat up the mold. Everything's hot. And so things are being injected in a hot runner, in some cases in a hot cavity for sure, because we use the temperature to cure the rubber to cross-link it. And as the material flows in, there's stagnant points, and there's the parts that move faster and slower, and therefore the energy of the tool, the heat, is through thermodynamics being soaked into the rubber, so to speak. And what we see is an onset of cure during the flow-in process. During cavity fill, we often see the onset of cure. And so we really have to look at this through finite element analysis, creating a volumetric grid of the entire flow process and really understand how it interacts with its side-by-side elements. And that's what computer-aided engineering flow analysis does. And our inputs are temperature, shear, and cure as it relates to viscosity at all times. So viscoelastic behavior. And what is that concept? Well, spring and dash pots, right? So spring and dash pots, spring represented by E, which is, the elastic component, and N or neta is the visco component. All right. So a lot of talks, I'm sure, over the last couple of days have been talking about this viscoelastic behavior. This very basic concept. But what we need to know is that all rubbers perform a kind of a pseudoplastic behavior. It's basically a shear thinning and heat thinning, where the viscosity is a function of shear rate decreases. And we also get some thinning because of heat. So right off the bat, we see that we're going to have to run some kind of dynamic viscosity, and we're going to have to look at it at various temperatures, because we need to understand what shear and heat does in that flow path of the injection machine. And in this case, we always look at it as a log-log. And John Dick gives a great talk on why we can look at this as a straight line as the power law in visco performance with respect to shear rate. And generally, we see all the rubber materials line up as a near or very straight line in ideal behavior, at least in certain sectors. Once we get past the paint effect, where we have filler polymer interactions, we see kind of a linear effect. And I'll talk about more of that as we get into this. And then we have the thermal set behavior, the curing, which is a thickening. If shear and heat thin, then cure thickens. If you think of it in terms of viscosity, we see as the cure degree increases, we see the viscosity go up. And we generally look at this as a log versus cure degree. And this is the method we tend to display that data. Now, the slope of the curve, the height of the curve, those all change depending on material. The cure system itself changes over time, because what we do get with rubber is bin aging. So this curve will actually, because of the reactive chemistries in the rubber, change somewhat depending on how long it's been since the material was mixed. And then, of course, there's lot-to-lot variation and a bunch of other things. And that's what certain rheometers are really good at is the QC and the cure degree behavior, and understanding that over the course of time and lot-to-lot variation. Okay, so if we take the spring and dash pot, the viscoelasticity behavior into account, and we look at it as a function of time under both strain and shear, Voigt-Maxwell created a model that behaves pretty interesting. And what we can see that in is by plotting the strain with time and applying a load to a material. What we find is the springs, if rubber were perfectly a perfect spring, which it is not by a long ways, in its raw form, then we would just simply load and unload and it would return to the same spot. But when we unload a material, there's always some component of loss. This is that double prime data that we see. And so as we run under quasi or semi-steady state performance in a injection machine, start-stopping creates different magnitudes of loss. And we have to understand and track that so that we can understand cavity design and mold design concepts. And so the viscoelastic behavior, the elastomeric behavior in general, has to be understood across these concepts. So let me walk you through the injection molding cycle. And I always like to start with that with taking out the cure effects. Let's look at a thermoplastic injection molding cycle. Let's look at one that's very common. And I'm going to give you this idea of what the viscosity or the thickening or thinning of the material does as a function of the cycle, of the molding cycle itself. So start of injection. So when we ask for a material to be delivered into the mold, into the cavities, to fill the cavities, and then all the way through the process to where the mold opens. And with no thermoset considerations, this is pretty simple. We basically have a melt of material, and then we have a cooling of material. And we hope to have that kind of, in the ideal case, a very straightforward flat line. But now let's add to this complication and now look at rubber injection molding. And this is conceptual, but now think of that flow of material through the flow path, through the screw and barrel, the nozzle, the runners, and into the cavity. Think about the cure. And what we really love is, if it were this simple, we would really have an easy time as designing for manufacturing. Because here we show the flow just comes in. There's no resistances. There's no change in viscosity. We see the cure just basically start, and it starts at max, and it's pretty much an on-off switch. It flows, and then it cures. But in real life, that's not the case, because we know that through the flow path, the viscosity is first going to be higher with time. This is with time, higher, and then it's going to start to see shear thinning, and it's going to come down because of the shear thinning. And then at some point, the onset of a cure is going to take up, and this arrow shows that the material is going to cross-link, cure, and we're going to see the shear thickening. So what that means is that it's critical to understand the viscosity as this function. And note that I'm saying that it is the change in viscosity with time with respect to the functions of temperature, shear rate, and cure. These are important things to understand. And that's where we use the Premier RPA to measure what's going on viscosity-wise under these conditions in the flow path. So flow is affected by cure, and gel point stops the flow. So we see the flow with viscosity go down, the flow goes up, and then that cure starts to take over. And at some point, we reach the gel point. And the gel point is really defined as the point where we have a cross-link network that is tied together. Each individual polymer, or at least most of them, are tied together in such a way that it's a resin now and will no longer flow. It's still elastic, but it will no longer flow. And so the concept is to make sure that we've filled the cavity completely. All the finite elements within that cavity are fully filled out. And when gel point hits, we have the ideal perfect part. And then the cure system will continue to cure and generate the finished article, the cured article that's developed all its full elastomeric properties. So going back to this quasi or non-steady state process, we have to understand that flow is not continuous, that this affects flow. And what happens to the rubber during that process upset, and what are process upsets? There's operator holdups, there's raw material changeovers, there's mold stoppages, cooling water stoppages, electrical power stoppages, go on and on and on. A manufacturing process would love to just have a machine that just kicks out parts 24/7, 365 days a year, and just, dropping parts out of it right and left. And of course, those are all perfect parts. They're fully formed. We ship them all out and we're great. But in reality, something will come up that stops this. And when that happens and we put the press back into order, some things happen. And going back to our model, what we see is that the viscosity, depending on how long the stoppage was, doesn't repeat the same path. There's multiple paths due to this quasi non-steady state operation. And so if the viscosity is changing, then the flow changes, which means the time cycles are off, which means that the cure starts and stops at different times. And so the machine's duty is to try to react to those problems. But injection machines cannot do that without having a fundamental understanding. And in many cases, we can take this material characterization and load it into injection machines, very modern injection machines. And the machine itself can predict and then apply, in this case, maybe a little bit more pressure to resist against the higher viscosity, which would then stabilize the flow, which would fill the cavity in a more concise time period, which would initiate cure at a more consistent basis. And so you would have a process window that is controlled. That's the concept. And that is really where we try to go to in design for manufacturability and why it's so important. But it all starts with material characterization, because we have to understand what the function of all of these aspects of the material have on the viscosity. Again, the function is based on temperature, shear, and cure state, okay? And so that's what we need to understand. So how do we do that? Well, with complex rheology, we do that, and the Premier RPA is your machine to get that accomplished. And what we can do is we can look at this from a simulation point of view and test every viscoelastic consequence with this machine giving us feedback. If we give it a certain shear at a certain temperature at a certain state of cure, then the machine can tell us what the viscosity of that is. And given a matrix of all the temperatures and all the shears and all of the cure degrees, we can then pick where the material is in terms of the viscoelastic consequence. And so again, staying kind of high level at this time, I just want to show you what we're going to head to if we use this machine and we do the material characterization, what can we learn about the process? And so let me start that by showing you, and I'll explain all these sequences, but from the time the mold closes, and excuse a little bit of the advertisements as we put this video together, you'll see the entire process. Imagine what's going on in that mold. And all the metal is stripped away. And we're looking into this. And first we saw the cavity fill. And now we're seeing in real time, 42 seconds, the curing of the material. And we understand now from a simulation point of view that this material, what's going on inside that mold. And if we can understand what's going on, then there's a lot of great things that we can figure out about that. So this is something we put together for the American Chemical Society show, where we cycled this tool over and over again. We had the exact same process going on in an injection machine with this screen showing every process was being run. The press was following exactly to the second, or even to the fraction of a second, all the things that we see here in terms of percent cured. And we were able to demonstrate, this was around 2012, how material characterization can really gain a lot of information about what's going on in the rubber injection molding cycle. All right. So that's where we're headed to. But how do we get there? And I think really the first aspect of how we get there is understanding injection process parameter windows. And you have to understand the cavity fill is a window of opportunity. That's really what it starts with. And then you can see in this graph, I mean, if we start to inject, we call it dosing volume, and we look at the article weight and cavity pressure over time, we can see that through the injection process, we fill the cavity, and there's kind of a Goldilocks concept to this filling of a cavity. You want not too little, and you don't want too much. Not if you want your porridge just right. You want the fill to be within this good straight section. Not filled is going to give you a degree of non-fills, defective parts, which then you have to inspect out, which is very costly. And if you fill that product, that cavity, with too much material, then we see the flash happen. What we see is excess rubber gets into the cavity and it's extruded out through the mold parting line, and flash is an unacceptable outcome and generally a defective part. So a window of opportunity. And this pressure curve, this is the pressure the injection press puts on the material to force its flow, has to be attenuated and controlled very accurately. And again, pressure equals the force that the rubber puts back due to its viscosity underflow. So pressure is the control of the viscosity consequences, the viscoelastic consequences of the material. So these are important considerations in terms of a window. And then in terms of rubber, it's not as simple as just filling a known volume. The compressibility factors and the thermal expansion factors, because things are changing in temperature, are very important. And so we have to take the understanding, in this case, the cure temperature with respect to the specific volume or the density of the material. And we note that in typical molding processes, there's kind of a cycle that occurs. We start at one temperature and we increase the pressure, then that enters the cavity and we see heating, and then we open the tool and we depressurize, and so on and so forth. So we see compressibility and thermal expansion as a very important factor. And obviously, we have to program that into the material characterization as well. And this helps us then, through this concept, adjust the pressures in the injection press to give us very good part quality performance. All right. Now, injection molds, why do we get non-fills? Why do molded parts sometimes show rough surfaces? And why do molded parts sometimes show burn marks right out of the mold? And it's all due to process window setting and the importance of understanding the material characteristics in setting those windows is really, often asked. And let me show you a couple more great videos of how flow path turbulence, for example, can show jetting effects and really make us want to change where we gate. If instead of gating here, maybe we wanted to gate from the edge so the material did not flow in this pattern that creates turbulence. And you can see that in the finished part by looking at the temperature and all the muddled, we have green and orange, we have the whole spectrum mixed together, because what we're seeing here is the mixing of the material created some temperature variations throughout the part. Where we see temperature variations, we're going to also see defects, mold lines. We're going to see knit lines. We're going to see a lot of different types of issues due to that turbulence. So, there's some things that we can do about lowering the viscosity, is more likely to cause jetting. So one of the things we may say is this is not an acceptable material for this configuration. If we can't change the way the mold is built, then we need to increase the viscosity of the material, which as a rubber chemist, there's 150 ways to do that. So we may want to go back and qualify a different material. Slower injection helps, but slower injection equals lower mold temperatures, which slows down the manufacturing process, which costs money, and nobody wants to do that. So here's a case where you're going to look at a change in viscosity of the material and choose a material with higher viscosity. So jetting creates those random non-fills, and you can always see that if you're an injection molder and you see that one time, on this cavity, we have a non-fill in the upper right corner, and then the same cavity in the next heat, it's in the lower right left-hand corner. You're probably seeing some type of flow path turbulence, and so there's ways to mitigate that. All right, so here's another case. Scorch. We know that rubber can be overcured, and in this case, we're looking at scorch where it occurs in the when it's finished here, filling the cavity. We see scorch actually measured in the CAE software. This is a factor of scorch from high in red to low in blue. And everywhere we see yellow and blue sections, we're going to see hot surface temperatures that have scorched the material. Looks like there's a real bad problem in the back here where we're going to see a very scorchy condition of the rubber. And what does scorch equal? It means poor elastic properties. The physical properties aren't going to be very strong here. This is obviously a type of a connector. So this is going to be a high wear point. If, a place where perhaps a seal will be broken and this part should be defective based on what we see here. So again, we can make some changes to the rubber cure states by slowing down the cure. If it's an organic, we might want to change the accelerator levels. If it's a silicone, we want to change the type of peroxide or add inhibitor if it's a platinum cure system. There's a lot of things we can do from chemistry. There's also some things we could do from gate location. In this particular case, I know the gate location was changed. They moved the part, moved the edge gating that you see here, moved it to one of these larger areas, and then they filled the part with the last place to fill at the pins, and pins are a good place to vent. And so they solved the problem by just moving the gate for the cavities. And again, designed for manufacturing. Before they made their first molded part, they knew what their defects were going to be. They changed the way the mold was going to be built, the way the cavity configuration was designed. And because of that, they were able to solve these problems. All right. Gate filling, trap gas burners, that's another thing that is an important process window. And, we really have to understand PV equals nRT. Pressure, volume, and temperature affects the rubber. And what we see is that in cases like this one, we have a big problem that comes from these two side pieces. And this creates some turbulence. It creates some outgassing of the rubber itself. Very important point. The rubber itself has volatilities. It's a polymer, and there's always a high degree of volatility in any kind of rubber compound. Organic, silicone, doesn't matter. And that gas has to go. You can vacuum the cavity. We always recommend in injection molding that we use vacuum. But what we see here is a place where the vacuum couldn't get to, and outgassing of the rubber created a pocket. And that pocket then is put under higher and higher pressure as this cavity fills. And it's low pressure, low pressure, low pressure. But then as this fills out and we hit that process window for filling the cavity, this then becomes a high pressure area. And we have to understand something about the PV-T relationship. When you do have a gas and you're injecting at high pressures, for example, 50 bar is very typical. If we assume that this was first room temperature, and then we're going to apply 50 bar of pressure, under that PV equals nRT, if the pressure goes up, then the temperature has to go up to compensate that in a linear fashion. If we go from room pressures, atmospheric pressures, to 50 bar, that gas is going to be 2,500 degrees Fahrenheit. So that red indicates a burner. And rubber can't hold that kind of temperature, so it burns the rubber away and really causes an unsightly defect, which is usually quite obvious. Those are non-fills, those are scorch lines, those are knit lines, those are defects that will definitely need to be designed away from in the DFM portion of designing cavities. And as we see, this is a single runner. If we look at multiple cavity performance, this adds much complexity to the design of a multi-cavity mold. Okay, so I kind of gave you that run through, right? And kind of looking at that and understanding this concept of high viscosity green through the flow process into the runner system and into the cavities, we see a change in viscosity. And typically we see viscosities that are quite high. Now, note this is a log graph. It's a little backwards because I plotted it this way. We usually see this turned around. We see the feed, is fairly high viscosity. We see the injection unit, kind of in this range. And then we see a drop off clear down to, just a couple orders. So 100 or sometimes even below 100 Pascal seconds in viscosity. But it's amazing that something that starts in the thousands of Pascal, tens of thousands of Pascal seconds, through shear thinning and heating, can come down all the way to almost single distance, digit kind of numbers. I made this blue to represent kind of water, because really we're approaching those viscosities of water in the injection molding process. But we start with extremely high viscosity, and the injection machine's duty is to break that rubber down through heat and shear and drive that material into the hot mold surfaces to get it cured properly. And we want this process to be as consistent, heat to heat, lot to lot, day to day, shift to shift as we can. And material characteristics will give us an insight as to the performance of the material and what the machine has to do to compensate. So here we are to our next section, material characterization. But as I promised a break, and it's approaching the top of the hour, I think, what do you think, Rick? A 5-minute or a 5-minute break or a 10-minute break? What do you think best?
5 minutes or 4 minutes and 30 seconds.
Okay, so let's start at the top of the hour at 11 o'clock, and I'll begin the real meat of this discussion, material characterization. So let's go on break, and I'll see you at the top of the hour.
Excellent. And if anyone has any questions that have come up, I know Rick has certainly gotten into some detail. Any questions, feel free to ask. When we get back, be a good time to answer them. If not, we will hop right into the next section then.
No questions, Rick. So I must be either putting people to sleep or I'm doing a really good job. I think it's probably the first rather than the second.
No, I'm certainly learning a lot. Christoph says, very interesting presentation.
Thank you.
I actually have our brand new intern here with me, and she's learning a lot as well. Yeah.
Well, the next two sections are more of a cookbook, how to accomplish this very thing. I've talked about what kind of you get out from it, kind of what the prize is. But now I'm going to show you the work.
Great. Now, how does this? Where's the software getting the computer model from?
So I'm gonna answer that in detail with exactly how we input. So I have a section, the last section of today. So I'll close with how you actually input the data. So great preview. That's definitely covered.
Okay, great. We do have a question from Joe saying, will the material characterization identify its gel point?
Yes, it does. And I explain specifically how it's done. I have a spreadsheet to help us understand how that's done. And you'll be getting that in probably about 25 minutes.
Okay. And then I think I can answer Christoph's question regarding the RPA correlation to high shear rates. The RPA we can correlate well to up to about 10,000. Beyond that, you would probably want to work something more like a capillary rheometer, such as the ARC 2020 or something along those lines, an LCR.
Yeah, that's exactly what I do, and I show how that's done. We test at relatively lower shear rates, and then we extrapolate to higher, and we do that quite effectively. And I know everyone's going to go, "Oh gosh." Well, we also proved it works, so we have the data in the bag.
Great. Well, then I'm definitely going to learn something.
We'll just another minute or so.
Yep, no problem.
Still drinking water.
Your throat does get dry doing these. I did 2 yesterday, and by the end, I was parched.
All right. Great questions. I'm glad I foresaw those questions in large part in the presentation. So far, to the audience, this is really kind of a I put this presentation together just for this first introduction of it. I'd love to have any critiques of it. If you think that I have a slide that's backwards or upside down or something, please let me know. First time I've given this discussion, so there's always a rough starting point. I'm hoping to maybe present this or some aspect of it at additional conferences. I think it's an important thing as we modernize manufacturability in the United States. I do believe that it is a curiosity that many have.
And to answer the most recent question, you will get a recording of this. We for those of you who have been in the previous webinars, we figured out why those were not automatically sending, and you should have received them in the last hour or so, or will in the next hour or so, any of the previous webinars. And you will automatically receive an email to a link to download the copy of this presentation, or not the presentation, the webinar itself. And you'll get that in about 2 hours via email.
I have also put 2 papers. So this comes from some papers, as I explained. A couple with one with SigmaSoft. We did a discussion in Barcelona, Spain, some couple years ago, and also with MoldFlow, another common CAE software. And so those papers are available for download. I find that the papers are better than looking at the presentation. As you can see, I put a picture up and I probably I talk too much, but really it's about what I say, and the pictures are helping to hopefully guide the mind. So the presentation itself isn't one of those highly written out presentations. I figure, nobody likes people to just read the slide, right? So I think the video of this presentation is more useful than the actual presentation. And with that, unless there's other questions, I see some coming in.
There's one more question asking if it's possible to utilize this approach in compression molding.
It is, although it has some consequences. Yes, you can, and you get some details out of it. There's only one type of two types of software I know that can do it, because that's a 2-phase analysis. You have air around your, your preform. SigmaSoft and Moldex 3D are the only 2 that I'm aware of today. I'll probably get corrected because, software is obviously updated all the time, but they can do that to some degree. However, how do you have to give the exact form of the preform going in. So that's always the tricky part, is how do you know what form it is? And where it's placed inside the cavity is extremely important. And those are manual items, so you don't get the repeatability. I wouldn't recommend it for design and manufacture. It might be useful for some just general mold building concepts. But injection presses, that's where the concept really comes to fruition. All right. Well, with that, let's get into material characterization. And we'll be looking at viscoelastic behavior, oscillatory rheometry equations. And this is where Rick will probably laugh at me, because this is probably my weakest subject, and rheology testing profiles. So again, we start with where we left off, just to get the mind rolling again. We're going from high viscosity to low viscosity across this format, where we're looking at the viscosity as a function of temperature, shear, and state of cure. So what does that really look like? And, we use dynamic rheology to study the shear thinning and heating in this log-log format. And we have to keep an understanding that the mixing imparts shear and reduces this viscosity, and heating reduces viscosity. And we see that now, obviously with the log-log plot, we see a straight line, but we see with increasing temperature that the viscosity comes down. And then the reactive or gel thickening, we see as the temperature increases, we see that the onset of the viscosity is sooner and sooner as the onset of temperature increases. And we start to take into this consideration a very important consideration for gel point, as I described in the injection molding cycle. It's usually in rubber. Everybody asks me, well, where does that happen? And it's usually, I've characterized 150 odd materials. I've never seen it less than 20%, but I've seen it as high as 50 or 60%. So it's somewhere in that range, and I'll tell you exactly how to find it. And I'll go through that analysis in a few minutes. So for your particular material, we can get a pretty close estimation of the gel point, whatever that is. Okay, so shear viscosity, it's really important to understand that it's shear rate dependent. This funny unit, reciprocal seconds is how we measure. So any time you see reciprocal seconds, you're seeing a shear rate. And we always see the viscosity decreasing with rubber. The slope of this line can change. And so on and so forth. Okay, so we'll see that. This line is straight when shear rate is a log. And I would say, if anything, that's a mistake here. You can see I'm showing it in logarithmic form, but I should probably put log here. It should be increasing log shear rate. With most materials, once we subtract out the paint effects and we're in that high flow, high shear levels, we generally see a very linear approach to the materials. Not every material, but generally that's what we see. It's a rule of thumb. And that temperature increase is very important to measure. As the temperature of the material increases through the flow path, we see that decreasing. And in dynamic rheology, I've worked closely with now retired Dr. Hans-Peter Ruoff. He's from Dow Corning, good friend of mine for many years. And he proposed a method of considering the viscosity of rubber compounds due to the paint effect. And really, it's a three-step process. And this can be done, of course, in a Premier RPA. And this is first a pre-shear mode, where we do a short but significant shear applied to erase the sample history. So all of our programs basically have this. You've taken material, a rubber material, you set it on the shelf, and you note the viscosity increases over time. And there is a degree of, minor strain that can be applied to kind of bring it back down to what it would be if it were freshened on a mill, or freshened in terms of running it through the screw and barrel. So this is the screw and barrel's duty, is to place on the material a mastication or a pre-shear mode. So we're duplicating what's going on in the screw and barrel right here. And so that's always the precept of all of our programs for the rheometer, is running this step. And then there's a structural rebuild. We always want to understand the time in which the material rebounds. And we look at G prime over a time sequence. Injection machines run pretty fast. We see less than a 6-minute cycle. So we don't have to run a long time sweep, but we do see in many cases the G prime of the material increase as time goes on. And now these two tests, step 1 and step 2, are generally run at low temperature. We run them at about 30 C, and so warm but not hot. And this is all in the pre-vulcanized mode. And then once we do that, and once we've kind of mimicked what the injection machine does, screw and barrel, the pseudo quasi-state steady state process, then we can run a dynamic viscosity sweep and get to the true viscosity of the material. Again, a very linear performance. I'm showing from 0.1 to 10 reciprocal second shear. This is in log fashion. And so we run this style. Now, the specific programs around this I'll be going through. This is just kind of a 10,000 foot view of this. And, we generally do a strain sweep through as, 0.1 to 100 reciprocal seconds is a good place to be. Okay. And then we can extrapolate out to higher shear rates based on that number. And I'll show you how to do that. So what can do that? Go back to the Premier RPA. All of these concepts, all of these steps are programmed in a Premier, a programmable RPA rheometer. All right. Keep in mind that we have to keep all of our programs have to be relatable to temperature, shear, and cure, because that's the function of viscosity. Oscillatory rheometer equations. Oh boy, I had nightmares last night about going over this slide. So if I make any mistakes, please let Rick know and he'll correct me. First of all, from a general point of view, the Cox-Merckx rule is very important to understand in terms of shear rate dependence. And it really states that the shear rate dependence of the steady state viscosity equals the frequency dependence of the complex viscosity. Or more simply put, in fact, I read that to myself 15 times last night and didn't understand it. So if you don't understand it, we're brothers. Simply put, the steady state shear viscosity at a given shear rate is equal to the dynamic viscosity at the same frequency. Now that gets me to a better understanding. But what you can really see it in is in these ideas of these equations. In oscillatory rheometers, the shear stress is a function of force over area. And the shear strain is a function of X with T. And we have the shear rate definition as a relationship to the shear with time. But the viscosity is a relationship concept of these three equations. And N star, which is the complex viscosity, is related to the true viscosity by looking at the shear stress over the shear rate. All right. Okay. So how do we calculate the shear rate? That's always, in an oscillatory rheometer, it's a function of time. It's at its maximal mark, the shear rate is different than as it's passing through the 0 point of arc, as things are passing back and forth in an oscillatory format. And what we find is the shear rate is time dependent by the oscillation frequency and the peak strain. And when we do that, we know that it changes by time based on cosine. But cosine's maximum number, its peak output, is 1 unity. And so what we use to determine the shear is always looking at the peak shear rate. So that's what we plot, is the peak shear rate. And for at least most of the Premier rheometers, there's kind of a motor limit associated with that. And the cycles per minute, the frequency, and the arc in plus or minus degrees has to be less than or equal to 3,000. It's an empirical number, okay? And that's the motor limit across what we can perform. So if we calculate that and we, for example, use the maximum, and we know that at plus or minus 90 degrees, and remember, I said something about decreasing the pain effect, and the pain effect is overcome by making sure that we are at high strain. And so all of our testing that we recommend is at high strain. And so we max the arc out at plus or minus 90 degrees. And it just so happens that 33.33 CPM is the magic number. And it's magic because when you consider that you go through this calculation and we find out that that 90 degrees is 1255 plus or minus 1255% strain, or 12.55 peak strain. And at 33.333 CPM, we come out at 3.49 rads per second. So that's omega. And we then do the calculation. We find that the motor limit restraint for high strain analysis is 43.8 reciprocal seconds. Okay, so that's the machine limit. And as I said, we want to be in the area of about 100 reciprocal seconds for this dynamic viscosity test. The machine limits is 43.8, but we can use that. And the big question was, can we do that accurately? And so we've looked at many different material characterizations, and we find that 43.8 is good enough. The lot-to-lot variation of the material is going to be greater than the inaccuracy caused by the slightly short shear rate limits imposed by the motor. So Rick, I'm going to pause. Is there anything on here that I'm falsely stating because you're the expert?
Didn't see any fallacies.
Okay, that is not my area of expertise. So good. I got through the most nervous part of my presentation right here. This was it. Wait. I think I've got to. Oh, okay. All right. Okay. Good. All right. I'm sure there'll probably be more details or questions about that, and I think we'd have to answer those offline, and because I need Rick's help. All right. So I promised you meat and potatoes. Here it is. Here's the rheology testing profiles. And it really is in 4 parts. There's cure kinetics testing that this is all under the material characterization. It's not one test. It's actually a 4-part series of tests. And I've got them labeled and I've got them detailed. So each one of these is going to take a separate sample of rubber. Okay, so imagine running a rheometer test for each one of these. So we got 3 plus 9, that sounds like 12. We got 15. It looks like we got 18 tests all in total. You have to do all 18 tests to material characterize. We start out with cure kinetics, because obviously we need to know how things cure. And we have to do temperature wraps to do this. And this is under something called McCosco relationships. It's the algorithms inside the CAA software that accepts this information and takes out the effect of the sample heating. So the sample size no longer matters. Well, as long as it's consistent and all those things that Rick taught you in his presentations yesterday. But what the algorithms do, because the rheometer itself is subject to the thermal heating of the sample, right? I mean, if you used a sample that had twice the mass, I'm sure that the heat capacity of the material would cause things to cure a little slower because the material would soak up more heat from the metal surface, the hot metal surfaces of the system. So obviously, part of the inputs are going to be things like heat capacity as well, and not just rheological properties. But when we look at the cure kinetics, and I just label them in program CK1 through 3, we're looking at 3 temperature sweeps at a reciprocal seconds of reciprocal 10 reciprocal seconds, well within that 48.3 area that we talked about due to the motor limit. And the premier rheometer is able to do 10K per minute quite easily. It's well within the control band of what the equipment can handle. We start at 90C for most materials because nothing really happens in rubber before 90C, and we run it up until the material is cured. So we run that, and the specific test that gives us the detail is VTA strain.
Hey, Rick, real quick, what was the name of the equation you mentioned at the beginning of that section?
The beginning of the equation.
Now, it was at the when you first started talking about cure kinetics, you referenced a correlation.
Oh, McCosco. Yes, maybe I introduced that a little too soon. I will be going through that.
Okay.
It's the algorithm. It's the algorithms within the computer software that take this data and convert it to material characterization data, which is in my last section.
Okay.
And you notice that I'm calling it out here as well.
Okay.
I'm introducing this just to show that this information has to be input into a computer somewhere. And the way we do that is through cross-Arrhenius McCosco algorithms.
Okay, thank you very much.
Yeah, focusing in on just the CK, notice that everything that we'll be doing is going to be a function of temperature, shear, and cure. And notice that here I'm doing a temperature sweep, doing a shear rate analysis. And one thing we are not covering here, but will show up in the graphs, is the state of cure. As we increase the temperature, eventually the rubber will start to cure. And so we are taking into effect this cure kinetics. All right. So what does it look like? So once we run the VTA strain, we can look at and put the data in, as I'm showing here, temperature, shear rate. This is the 10 shear rate range. It's always the shear rate. And then the viscosity at that given temperature. And so we're going to be plotting this, all three, CK 1 through 3, at these various temperature rates. Notice as the temperature rate increases, this is our 10K per minute. Notice that the data is much shortened. Well, the material is heating up so fast, the viscosity creeps up from, in this case, around 80, all the way up to about 23,000 Pascal seconds very quickly in just a few seconds. But when the temperature rate is slower, of course, we see a lot more data. And so it's always important to have a temperature rate that kind of measures. And in some cases, we might do a 1K per minute, or sometimes we have to go to 20K per minute. This rate worked out very well for this particular cure speed for this particular material. And this material is a platinum cured LSR silicone. Okay. But if you're using perhaps a tire material, you might need to increase the rate because the cure system would be much slower. So the rates are adjustable, is what I'm saying. And so if you take this data and you plot it, this is what we see. This is the viscosity with temperature actually plotted. And then you see the three curves for the 2, 5, and 10K temperature increase per minute range. And we start to see this. Now, in the inputs with mini software, you really have to put everything on a basis of state of cure or cure degree, where we're actually limiting. We would normalize these curves, and we would call the x-axis a 0 to 100, and that would be the percent degree. So depending on, for example, mold flow requires you to input this data, whereas MoldX 3D and SigmaSoft requires you to input this information in terms of percentage cure. So we do a lot of this analysis in a spreadsheet. We have to, because the inputs require different formats of the number, and formatting is always a bear for the different softwares. But once you buy a software, you get used to that format, and you can write up conversion programs that give you that detail pretty well. All right, so that's cure kinetics. Let's now focus a bit on curing viscosity, CV, curing viscosity 1 through 9.
Real
and
quick,
now,
can I interrupt you?
Ahead. Go ahead.
We had a question. What strain were you using on your cure kinetic VTA?
Well, we were using strain. I think we were using 1 degree of arc. I don't know the degree of strain that is. You could probably tell me.
Yeah, 1 degree should suffice. Thank you.
Okay. And in curing viscosity, we use a little higher one. I think we use 3 degrees. We have to go to 3 degrees to push the limit, the motor limit. Everyone asks me, Why do you go 1, 10, and why didn't you go 100? Well, that's why I covered the motor limit. 43.8 is maxed out. That's the most I can do. So we're running the cure viscosity with this equipment, which gives us these. We have to do a sweep of various shear rates at various temperature ramps, and what we're going to get feedback is the viscosity changing as a function of temperature, shear, and of course, as the temperature increases enough to kick in the cure system, we're seeing this viscosity change with cure. So we run the set of 9 tests, CV1 through 9, under this characteristic. All right. Keep in mind, we do that. We freshen up the material first. Okay. We do our structural rebuild study first, because that gets plugged in as well. And the timing between these tests are very important. These are separate samples in each case. All right. And so let's get into what that looks like. First of all, this is a specified series of tests that inputs to the Cross-Arrhenius-McCosco reactive viscosity models that are inside the CAE software. Okay, big fancy names, but this is, you select Cross-Arrhenius-McCosco, and it's going to ask you for all the individual data points for this. And then if the heat capacity is known, and it better be known because it's important, the test series uses an overlay viscosity as a function of shear rate, temperature, and degree of cure to cancel the effects and combine the Gibbs free energy impact of both enthalpy and entropy. Okay, again, I read that 6 times last night. Let me try to just explain it easily. When we do these temperature ramps, there's subtractive calculations that can go together. And in combination with the heat capacity of the material, we can start to understand the entropy and enthalpy effects. And the best study, the story that I give around that is when I was testing very extreme conditions of molding, the process window, and I started injecting platinum cured LSR into an injection mold at extremely high rates of speed, unbelievably high rates of speed. The injection speed was set so fast, I think I might have damaged the equipment. I don't recommend it. But when we did that, we were able to inject LSR silicone into a cold mold. It was actually cooling water was on the tool. It was a plastic mold. And the temperature was about 38 degrees Fahrenheit. And we could cure the silicone just through entropy effects, through mixing high shear rates, extremely high shear rates, numbers that were probably in the range of 200, 300,000 reciprocal seconds. And we were able to cure it in less than 5 seconds without even heating the mold. That's how important entropy is. When we start talking about high pressures, high flow rates, fast fill rates, so that we really have to understand the Gibbs free energy impact of both enthalpy, the heat aspect of curing, and the entropy, that of mixing. So things, when they're under high shear, they cure faster. That's why LSRs cure so quickly and why injection machines are so efficient. All right. So cure viscosity would look like this. As we're starting to see, I've broken this out into the 3 shear rates, low, medium, high, and we're looking at these viscosities, the N star value, across the tests, and I've got them listed here, and you can kind of see all this individual data points. All these balls have to be input. Now I've printed it out. You don't put the graph into the computer. You put the individual data points. So it's a cut and paste from a spreadsheet over to the CAE software. All right. And that's what that looks like. Curing viscosity gives us that Cross-Arrhenius-McCosco input. And then gel time. So focusing on gel time, that's where we're going to be taking a look at time at a constant temperature. These aren't temperature ramps now. And we're looking for a long drawn out. And in this case, we did 1,000 hour seconds. Now, the temperatures need to vary. You can use 80, 100, 120C for maybe a fast cure material, but you may need to increase the temperatures to get, a profile that cures within 1,000 seconds. So we really slow things down and use lower than typical molding temperatures, because remember, the path of the material through the mold starts in the screw and barrel, and that's at very, just slightly above room temperatures. So we have to choose gel time analysis across the span of the temperatures within the flow path of the injection machine itself. And so I've truncated, this is and so on down here, but you can see we've put this in terms of degree of cure. So we've, this is a very small number, 1 times 10 to the 12. So we're essentially starting out at 0 degree of cure, 0 degree of cure, and we reach 100% state of cure. We go from -12 to e to the +12, and we've in 1,000 seconds always reached full state of cure. That's the check here. And then we can take this data, cut and paste the individual data points, and we can create graphs that look like this. And note that they're all based on a state of cure measurement, 100%, and they're all come to equilibrium 100%, or put as a basis is a better way to say that. And that's how we have to input it into many of the pieces of software. So this becomes the cure degree curve. All right. And in a minute, this gel time is taken from this type of curve, and I'll have to go to the spreadsheet to show you how that's done, but be patient with me. I'll show you how to figure out where the gel time is. So then the last series of tests, which is the pre-cure viscosity, are now frequency sweeps. And again, the premier rheometer can be set up to do this. We do a frequency type analysis. We do a 90 degree of arc. Remember, we're trying to defeat the paint effect, cancel out the filler or polymer interactions, pretty much just like we see in the runner system of the mold. And we're running a high degree of arc with 30C, and we're looking at these frequency sweeps across 1, 5, 10, 15, 20, all the way up to 33.3. Why 33.3? Because at 90 degrees arc, we've hit the motor limit, and we run across 3 different temperatures. What does that look like? Well, here's the raw data as it's put in. I don't think I've put in all the data. You notice that I'm up to the maximum shear rate of 40.38 across the bounds here. And so that's great. But I told you that we extrapolate this data. So hang on a second. The way we extrapolate that is plug it into the spreadsheet. We graph out, and knowing that we put this in a log relationship, we do a power law, and we plot out the equation in power law and the R squared. Note the high R squared correlation. And assuming we have something greater than 0.98, the calculation steps are, okay, add power lines, trend lines. We're going to check that R squared. If it's high, and in this case, in almost every case I've ever measured, they were high. The only times we had problems is when we didn't check, we didn't choose our temperatures correct, and we went too fast or we went too slow. So we just adjusted the temperatures. Instead of 30, 40, and 90, maybe you use 50, 70, and 120 or something like that. Anyways, you plug those in, and what we do is we normalize the slopes. And so in this case, we take the slope numbers, this minus 0.459, minus 0.558. We average and normalize. And then we plug those equations back in with a normalized slope. Notice that now the slopes are all normalized, holding the same start out factors. So the y-axis crossover comes from these equations. And so now we've extrapolated out. We can now take that data and use the calculated viscosity based on those equations and create numbers that show very close correlation because of the high correlation. And we now plot out calculated viscosity. And now we can look at it from 1 to all the way up to millions of reciprocal seconds, because we're assuming that this extrapolates, this series of data right here, this was the limit of what we could test, extrapolates all the way through the power curve down here. Now, I understand that that's not exact. And I understand that, there are other rheometers that can get down to this area. But I also find that when we increase the shear on materials, we start to have interference with this problem of entropy and how it will actually start to cure the material. And so I'm not sure it's more accurate. You can get a number down here, but I'm not sure it plugs in well. And in addition, we've run studies after studies to see how close this type of extrapolation is to real world. And it's passed every time. So I would argue that although extrapolations are not great in the world of science, in this case, with such high correlation factors, it's close enough for a good, clean material characterization. All right. I'm sure there'll be people that are probably doubting me. So I'll give you some words of advice. Precautions for high shear viscosity testing. These high shear tests tear the plastic membrane. So the first thing is always put your plastic on top. And the bottom is the motor turn. Use nylon because it's the most flexible. So I only put plastic on one side. Otherwise, you have effects of the plastic, especially when you're turning at plus or minus 90 degrees. So always just use one-sided plastic. All right. And then because you don't use plastic on the bottom and the rubber is basically getting into the shaft area, you have to change out your rotor O-rings quite often. And so you weigh out a sample precisely to minimize the overflow. But then after, you're going to have to change those things out and do a re-self calibration constantly with this. So it is a time-consuming test, and keep in mind. And then for the dynamic viscosity, the PV tests, it's really hard to take the material out until you cure it. So we just run a cure test afterwards just to cure everything out and clean out the rheometer. Because remember, you're not using plastic on the bottom, so the rubber's touching the metal. And you can get some adhesion and stuff after those long tests. So I would recommend running cure cycles to finish things up. Okay, so that takes us right where we want to be. We're running to the finish. And I talked about the specific rheometer tests. Now I'm going to teach you how to input that information into the CAA software. And then depending on how much time, I have lots of output examples. We don't have to go through them all, but some videos, more videos that give you very specific runouts of how this data is used and how you can use it to design for manufacturability. All right, so let's get into that.
Before we get started on the next section,
Sure.
We did have one question asking why is it necessary to average the slope factor?
Well, otherwise you get some weird data because it is extrapolated, so the data is not perfect. I'm going to go all the way back here. You can see the slopes of these lines are not perfect, and you can see that, of course, in the numbers as well. We have a 0.45 minus 0.459 and looks like 0.558. And that's because the data is not perfect. There is error in the equipment. There is error probably due to the sample. In many cases, we've run this test more than once and we've averaged the plots, and that actually helps. Run the test 3 times and you get a correlation factor that's usually 4 nines. So you can improve this. But we do see some slope variances. And if you have slope variances and you were to not normalize the slope, then what you'd have is some crossovers. Now, that's bad because the algorithms, the McCosco specifically algorithm, if you have a crossover, you have a divide by 0 in the math. And a divide by 0 is bad in any math. That's infinity. So we can't have crossover. So when we normalize the slopes, we negate crossover. So I do that primarily because the algorithm, which of course is also an estimate, An algorithm is not a real life factor. So we have to understand that we have to normalize the slope so we don't have a divide by zero in the numbers. If I ever see these lines cross, what was it, that movie Ghost? Streams can't cross because it blows up McCosco algorithms. That's what happens. I think of that funny movie. So I hope that helps.
Perfect. Thank you very much.
Other questions?
Yep, I think that covers everything. And then just time check, we got about 20 minutes.
Yep. So I'm going to go through another short factor. This is, we just got through the meat and potatoes, but how do you put that data in? And what do you get out of it? And so, I talked about things like cure degree, and you input all this data in. And then what we get for an output is reaction kinetics. This is the Kamal model, which I'll go over. And basically, once you put all this data in, it will calculate through these algorithms these constants, A1, A2, E1, E2, M, and N. And this is the material characterization constants. You can input these manually, you can go measure these out, but all the software has the ability to input the raw data, and it will calculate for you this. This happens to be, I believe this happens to be a SigmaSoft that I'm showing an example of, but all the CAA software has this ability. And this is what you're trying to get out. You're trying to get this screen, you're trying to get it to calculate all these numbers. So we input data fitting, reaction kinetics that we were talking about, and we're putting all this data in point by point. You can see the points that are input into the software, and it's taking this number, running it through Cross-Arrhenius-McCosco, and it's generating calculated curves that you're seeing here. And then it's used also in the finite element analysis and the spot-by-spot review of the flow path, and so all of that is input. Your CAA guy can do this with his eyes closed. I'm sure he's done this 100 times. You have to choose the correct models. All of the stuff that I've given you is based on Cross-Arrhenius-McCosco. That's why I keep saying it, because somebody will say, no, I don't like using that. I just want to use the Arrhenius-Dungshi. Well, good. Then you need someone else to get the data for you, because that won't work. This data is for Cross-Arrhenius-McCosco. Use it or come up with your own programs. And maybe Cross-Arrhenius-McCosco isn't the best one. I found it was. We've looked at a lot of them, and it gave us plus or minus 5% of real life. So Cross-Arrhenius-McCosco works well for us. So data fitting complex rheology, the viscosity curve, at various temperatures, we also run and put in. And note that what we do is we're going to run this at different degrees of cure. We started at 0, 5, 1, 2, 20% degree of cure. And so we input that data. And so we're starting to get close to the gel time and understand that. But there's other inputs to the simulation. Remember, I told you PVT is very important. So we need the specific volume relationship with temperature and pressure. So we have to, that's not coming from the rheometer. It's coming from other test equipment. So we send out to a third-party lab and we get this data and we look at it in the cured specific volume and the uncured specific volume, because it is slightly different. And that's very important. So we have these other inputs like specific volume, and we input that into the software, and it starts to plot graphs out, and also is used for things like gas analysis, shrink analysis, part dimension, and all of that is very important, as well as the compressibility factors, all are related to this, which I already covered in previous areas. So. And then I said it's very important to have specific heat, and we have to have specific heat of materials because polymers are compressible. Their specific heats change with temperature and time and pressure. And so we run, usually multiple pressure specific heats and multiple temperatures, and we can relate those. And again, we have to input that into the software like we do that I'm showing here. And so all those data points are input. And so these algorithms are soaking up all of these data points and kicking out these material characterization standard numbers. Now, how does it actually do that? And what is the math behind it? And that has to do with computer modeling. And again, Arrhenius, Cross, McCosco. The Arrhenius model takes into account temperature effects as viscosity occurs to change with temperature. That creates something called N naught. And then that is used in the Cross model to calculate N prime. That is then used in the McCosco model. That's why I always refer to the gel formation effects. Cross takes into the shearing effects, but McCosco takes into the gel formation effects of both the Arrhenius Cross model. And so we have the stepwise approach for the computer modeling in an algorithmic format. So we start with Arrhenius, we finish with McCosco, and we have a very accurate model that then can be put into the cure rate or the Kamal model, which gives you the change in cure with the state of time with respect to both the Arrhenius and Cross conversion factors. And all of this stuff is plotted in a way that we do 6 equations, 13 unknowns with 3 variables, and you know what those are: temperature, shear, and cure rate. And for each element of the finite element analysis, we factor those in at all 6 sides of the square. And there are some studies that use cylindrical analysis, but I'm showing here a cubed analysis, a finite analysis. And I have references for all this. But you can see for each side of each cube, for each finite analysis, we have to solve for each millisecond in time 6 equations, 13 unknowns with the input of 3 variables. Wow. So computations with CAE can take hours and hours, if not days. Modern computer equipment generally does it inside of an hour to do a full process review. But that's what's going on in that calculation mode. And so we can now, with Kamal, look at the change in viscosity with time, with the function of temperature, shear rate, and cure. And so how do we do that? Well, I can show you one example. And this is an example of how we run it through the spreadsheet. And we actually plug in these calculations. So I give the yellow as the input. And what we do is we input temperature, shear, and state of cure, alpha. And we plug it into all of these models, which then plugs into the Kamal model. And we're able to generate the key constants, the material character constants in this regard. And I'm going to go ahead and pull up. I'm hoping everyone can see this. Can you see my, this is my Excel spreadsheet? Yeah, good. And what we see here is these are just inputs. And if I run this through every combination of alpha, cure rate, cure degree, shear rate, and temperature, then I can create these graphs of every conceivable process window within the injection machine's realm. And I've done that here. And then I also promised to talk about gelation point, which is the point during which there is a viscous liquid becomes a cross-linked gel or rubber. I already said that. And it is precisely the point where the tan delta becomes the frequency independent in a dynamic rheology measurement. But it can be approximated in a very useful way, and that's what I'm going to show you. When we look at G double prime subtractive peak measurement in the gel time test 1 through 3, which I previously described.
We're currently on the next screen. There we go.
And if we look at the gel time analysis and we look at the raw output of GG in a spreadsheet, and we plot the G double prime and G prime data from those GT 1 through 3 tests, then we will see in the G double prime data a crossover, a peak. And we note that at that peak is the changeover of the, that is the gel limit. So if I'm sorry. Thank you. Again, we see the graphs and we see G double prime and G prime plotted. We're seeing this at various temperatures. Notice that at various temperatures, the gel time changes. And these peaks, as they respond to a time below, in this case, looks like the time is about 26 seconds. If we go up here and we find 26 seconds, this gel point is 36.7%. And that's how we find the approximates, is these peaks. These changeovers indicate that the material is gelled. And so that's how we determine gel time. Not jail like in they should throw me in jail. I mean GEL, like, you know, gel and polymers. Okay, now I got to go back and pull up my presentation and hit this, which should bring it up and take you to the outputs. And I put this output by temperature, and I put it in terms of viscosity log versus shear rate versus cure degree to show you every point at which within the injection flow realm and how the viscosity, in this case, a silicone rubber, changes with temperature. And you'll note that as I change the temperature, that the graph plane is moving. And I can move it up and down, back and forth. And what I can do is show you the viscosity of the material in response to shear cure degree, okay? This is now being shown across the temperature range. So in fact, I have characterized this material in multi-point analysis across the entire realm of what the injection machine would expect to place on the material in terms of temperature, shear, and cure. And now I have this material fully characterized, and I see the variation in viscosity from gum to oil of this material, and it's characterized. So what does it tell us? Well, one of the useful ways to looking at how well this will work is what's called a lapse analysis. You take a spiral mold and you inject the material here, and it spirals and spirals and spirals, and you simulate this with the material characterization data, and you count the number of laps per second for these two materials. This is a material, this is a different material. You simulate this, and then you go set up your injection machine to perform those exact same constants. 1000 psi pressure at this point, mold temperature is 150 C, and your initial temperature of the polymer, so your screw and barrel is set at 30 C, and you run it, and you count two things. You count how fast this cavity filled up and how many laps per second, and it better equal. And normally when we run these material characterizations, we're plus or minus 5% of this number. And we always go back and check it, make sure that our material characterization was performed right. And this spiral analysis really gives us that detail. So let me talk about a Sigma soft validation that we did. And there's a lot more details about this in the two papers. So if I run out of time giving this, it's not a big deal because you have the papers. I have 5 minutes left. So let's just see if we... Okay, so I'll just run through a couple of things here. So the first thing we have to understand is the complexity of mold design and heaters and all of that. And all of that has to be plugged into the CAE, not just the cavity design, but the entire mold. And we have to understand that we can, in an analysis, strip away all the metal, and we look at something called a shot glass in this case. And this is a 32-gram shot, so it's really a test case. We can look at pressure of fill, as I described earlier, and use those material characteristic constants to really give us an accurate idea of the degree of fill. This is a pressure curve, and you notice that the pressure is very high here and ends up being quite low in the cavity, and the last place to fill is always the lowest pressure. We can get a blow up of that and look at fill from a different angle, and we can see the pressure increase in a different way. We can see the pressure increase here, the cycles and so forth here. Again, even a closer up view of just the cavity, and that's the one that we really care about. And we can see how the flow dynamics create differences in flow. And this is a shear stress analysis, and what you're seeing is red as being high shear straight. And where pressure differences are the max is where we have shear stress differences. And these show up as defects. And so this is kind of a defect analysis. In fact, if you take it to 99% cure, fill, I mean 99% fill, we start to see some really red areas. And if we completely pack out the part, we see that no matter what we do, we're going to have some high shear stress areas. In fact, this is an actual part, and this is an eclipse photo, and you can see in this photo the actual owl eyes that appear at these relative directions. You notice that they're kind of in this 12 o'clock, 3 o'clock, 6 o'clock condition. So it proves out pretty well. And, we can really analyze in real time what's going on in terms of fill, and that relates to cure time analysis. We can also look at time versus pressure. We can also look at pressure effects of viscosity, and we start to see that as there's stagnant flow, there's in filling the cavity, we see some viscosity increases. High viscosity is in red. We can see that in a more close-up condition. Stagnant flow causes problems, so we always want to make gate locations and things ideal. And we have a 2 order of magnitude difference between the red and the blue, so stagnant flow really does occur. We see those effects on shear stress again, and how those stagnant flow areas can cause shearing and defects. And we look at those. Again, you're going to see that primarily right at the end of the flow. We're going to see temperature analysis. I'll skip. We're going to see how that temperature analysis adjusts the cure degree. And what we'll see is a very fast cure cycle here. This is not real time. And we see how the cure occurs towards the outside, inward, through the cut throughs of the parts. So there's a lot of details that we can get, and we can see problems. Here's the close-up of the cure degree. All right. And that's pretty much taking us to the end of the talk. So all of that rheology data from the series of tests of material characterization gets placed in this CAE model. This case, this is SigmaSoft, but we've done this in Mold Flow and Mold 3D, and we have some great case examples of those, which you will see in the handouts. So while I did go through this last part of this quite quickly, I have 30-page handouts on specifically how we tested and what the accuracy was to real world of our material characterization. And we really passed the test each time. Okay, I think we're finished.
About 20 more seconds. So thank you very much, Rick, for joining us. That was quite a lot, and I think everyone agrees we learned a lot and a very interesting topic. So
if they need to contact me, I would have them go through Alpha and or find my RDAbbott company on the website.
Yep. We'll be sending out a follow-up email, and then Rick will probably be as well. So thank you.
Yep.
Thank you very much, everyone, and have an excellent rest of your day.
Very good. Thank you.
Bye-bye.